So today I want to give you an introduction to chapter 12 and all the different types of problems that we'll be doing with this. So chapter 12 has two parts in it, and we're only doing the first part of it. We are focusing on 12.1, 2, and 3, which are three parts of this chapter talking about static equilibrium. And static equilibrium is, these problems are actually among some of the easiest that we'll do this year because once you get the knack of them, the analytical pattern is pretty straightforward and continues from problem to problem. Just geometrically, they get a little bit nasty after a while. So, what is static equilibrium? Well, hopefully you remember from our earlier studies that equilibrium, at least in the sense that we've said it before, has meant a net force of zero, right? An acceleration of zero. Now, if we're going to put it in our new context, an acceleration of center of mass of zero. And it's static, meaning that the object is also not moving, right? Because there are two types of equilibrium, static equilibrium and dynamic equilibrium. In physics, a dynamic equilibrium would be an object moving whose center of mass moves at a constant velocity. Now, what we need to do is elevate this now that our masses are no longer point masses. So the condition for static equilibrium is no longer just that the net force on something is zero and its velocity of center of mass is zero, but also we need the net torque to be equal to zero, right? Because not only do we not want this object to translate or change the way it's translating, we don't want this object to rotate or change the way it's rotating. So the four conditions for static equilibrium then are net force of zero, velocity of center of mass is zero, net torque is zero, as well as omega, the angular velocity, being equal to zero, right? So things are not moving and they are not going to change the way they're moving. So now let's just take a little bit of a tour through these types of problems. And here you see the easiest of these types of problems. It's functionally a seesaw, right? I have a centimeter ruler, actually a 12-inch ruler, balanced on a Keurig cup, and two Keurig cups here at the side, and this thing is in balance. And that's another nice word for all of static equilibrium problems, is that the system is going to be in balance, right? And so here, not only is the net force equal to zero, but net torque is equal to zero. So let's look at those two conditions independently. So if we're looking at this, what forces exist? And hopefully you said that there are four forces, right? So we're going to have the weight of the Keurig cup over here acting down, the weight of the Keurig cup over here acting down, the weight of the ruler acting down, which is usually one that people forget, and that's acting at the ruler's center of mass, as well as the normal force upwards on the balanced item. So the object in question here is the ruler, not these other items, right? That's the thing that's maintaining a balance. And so it must be that the weight of all these things downwards is being balanced by the normal force upwards, otherwise there would be an acceleration in the vertical direction, and there are no forces acting horizontally. In terms of torque now, the normal force here is not going to create a torque because here the pivot point is exactly where this Keurig cup is. So by definition, this normal force cannot cause a torque if this is the pivot point. So what about our other three forces? Well, the weight of the ruler happens to be above the pivot right now, which is why its lever arm distance would be zero and it doesn't cause a torque. But these two things, their weight forces are not acting through the pivot and each cause a torque. So it must be that these two torques are equal magnitude and opposite in direction. This one wants to get it to spin this way, this one wants to get it to spin this way, and they're canceling out. Now, these are two identical objects, so it should make sense that because their weights are the same, that if we want the torques to be equal magnitude, that the two lever arm distances are the same. If I were to move one of the Keurig cups inwards, boom, there you go. The system is no longer in static equilibrium. But what happens if I wanted to balance two things of unequal weight? Well, I would still need all those conditions to be true, and you'll have to pardon me for a second because this ruler is rather flimsy, right? Let's say I had this, which is filled with water. If I put this on the end, let me see if I can get it balanced. It's a little harder. There we go. Once again, static equilibrium. These two weights are not the same, so if those two lever arm distance, or the two torques have to cancel out, the two lever arm distances can't be the same, and clearly this one is more massive. This is the principle behind a balance, right? A triple beam balance, or one of those old-timey balances that you may have seen. And so this is the seesaw problem is a classic static equilibrium problem. It gets a bit more interesting if your object is not uniform like that one was, right? If I try and balance this at the middle, boom, no good, because if I were to figure out where the center of mass of this object is, it's probably somewhere over here. So the weight force for the t-square right now, because it's not acting through the pivot, would provide a torque, right? But if I were to find where that center of mass point is and put the pivot point under it, now the weight force for the t-square does not provide a net torque, and therefore the system is in balance. So kind of scaling upwards now, from there, you have my two Lacroix columns. If I put that there, the system's in balance. It's a beam, right? So here's the thing, what forces are acting here? Well, we have the weight force from the ruler acting downwards, and the two normal forces acting upwards. So these two normal forces have to cancel out the weight, right? But how would I find out what each of these normal forces are? Well, it would seem logical that the two normal forces are identical. And actually, right now they are. But if I were to put, say, objects on my beam, oh, I don't know if the line is going to stay. All right. I'm going to tell you now that the two normal forces here are not identical to one another, but the system is still in static equilibrium. And we're going to learn how to calculate those two normal forces. Now, I know it seems so trivial, I'm balancing lines and Keurig cups on beams, but I mean, this is the basics of bridge design, and most things in mechanical engineering is based on this chapter, so it is actually really important. Now, you will also notice something as well, that the beam bent when I put the weight on it, right? So this is what's called a load-bearing beam now. The lime is the load, and it causes deflection. That's actually what the end of the chapter is about, 12.4 and 12.5. We're not going to talk about those. Those are engineering concerns, and if you go into mechanical or civil engineering, you will learn so much about elasticity of materials and shear forces and Young's modulus and strain and stress than you will ever want to know. But for physics, we're not going to talk about them. But the basics of this is assuming this object is rigid and it doesn't have any flexibility, and then what you'll learn in engineering school is how to layer on those complications. We are not going to layer on those complications here in our conversation. So the structure of a beam and how it bears loads, that's a very important consideration for chapter 12. So let's take a tour around. We'll look at some other examples. So here you go. I've got another classic example of a chapter 12 problem. And I know this sounds so ridiculous, but you'll notice here I have a crane, like a beam, right, that's tied to a string that's supported up here, and off the front of it, there's something hanging. This is functionally a crane, folks, right? Like if the mechanism was such that this rope would be attached to a motor to pull that up, and the object is pivoted over here, that's the functional equivalent of how a crane works. It's also, this device is also called a boom. And for those of you that are sailors, you know that word because that's the crossbar that holds the sail in place. And so these problems we're going to call boom or beam problems. And so if we look at the forces there, we have the weight acting downwards from the load, which is just a random half-filled water bottle. I'm going to have the weight of the beam itself acting down, this tension acting there, and then we're going to talk about the pivot forces that are acting there. And that's a really interesting problem that we'll spend a lot of time on later in the week. And then one other problem we can look at, let me just grab some books, okay? Right? Because we're talking about equilibrium, right? I got 3 of my Harry Potter books here. if I put the book out over the edge, notice the system is in equilibrium, right? But there's a certain distance I can go out, and then the books will start to tip, right? But I don't have to just move them out as a mass. I can move them out differentially and get them to not tip. And there you go. That's sort of an interesting thing there. And so what we're going to figure out is how far out you can get this extended grouping and not have a tip. Now, I just did it with 3 books, but we're actually going to look at a general situation of n books to see how far out we can make that system go. So, what we're going to learn in the next video is the basics of the analytical method for chapter 12. And it functions a lot on issues of center of mass, as well as thinking about torque when the pivot point isn't really obvious. On some of the devices, like for example the Seesaw, the pivot was super obvious. On this beam problem, the pivot isn't really that obvious. Same thing with the books there. Until they tipped over, the pivot wasn't that obvious. And so we'll look at an analytical method that will let us look at these situations in order to see how we're going to approach the problems. But if you can just internalize the steps of the method and be really rigorous in your process, you're going to find that these problems are actually quite straightforward.